Welcome to this explainer. Today, we're unpacking the absolutely fascinating solid-state physics that allows solar panels to generate electricity. I mean, the science happening right above our roofs is literally nothing short of extraordinary. We're going to break down this microscopic quantum dance that makes solar energy possible, using the actual physics and historical data to guide our way. Let's jump right in.
So, have you ever actually stopped to wonder how a completely stationary device captures sunlight and kind of magically turns it into the electricity powering our homes? Think about it for a second. Most of our power generation relies on massive turbines spinning, boiling water, combusting fuel, the whole shebang. But a solar panel? It just sits there. It's a silent, motionless sheet of glass and silicon with absolutely zero moving parts. Yet it operates as this relentless engine. To understand how this invisible mechanism works, we really need to trace its origins. Now, while solar power definitely feels like cutting-edge modern tech, it's actually deeply grounded in 19th century physics. Our timeline kicks off way back in 1839 with Edmund Becquerel's discovery of the photovoltaic effect. Fast forward to the 1880s for the first solid-state cell. Now, sure, it was highly inefficient and mostly just used for light meters in photography, but it was a start. The true revolution, though, the real foundation of modern solar, hit in 1954 when scientists at Bell Labs developed the very first viable, highly pure crystalline silicon cell. Okay, Section 1, the photovoltaic effect. Let's look at the spark that starts it all.
Simply put, the photovoltaic effect is just the basic physical process where sunlight strikes a semiconductor and directly generates an electric current. But what does that actually look like? Well, sunlight isn't just this continuous wave of brightness. It's made up of tiny individual energy packets called photons. When these photons strike a specific type of material, our semiconductor, they transfer their energy, literally knocking electrons loose from their atoms.
You can think of it kind of like a microscopic game of billiards. When the right photon hits the cell, it penetrates the material, collides with an atom, and transfers its energy to an electron. That gives the electron the exact boost it needs to escape its normal position. And once it's freed, that electron becomes a mobile charge carrier, totally ready to flow through an electrical circuit and do some actual work. But to see why silicon is the absolute perfect canvas for this game, we need to zoom in a bit closer.
Which brings us to Section 2, the silicon crystal.
Take a look at the incredible symmetry of this silicon crystal. Silicon is actually the second most abundant element on Earth, and in a pure crystalline solid, every single silicon atom perfectly shares its 4 outer valence electrons with 4 neighboring atoms. It creates this highly organized, tightly bound lattice structure. When a photon of light hits this lattice and dislodges a negative electron, it leaves behind an empty space in the atomic bond. We call this empty space a hole, and it actually acts as a positive charge carrier. But here we run into a major roadblock. Pure silicon is in a state of perfect equilibrium. Because all those electrons are so tightly bound in their covalent bonds, pure silicon is actually a pretty terrible electrical conductor at room temperature. Even worse, if sunlight knocks an electron loose to create that electron-hole pair, nature tends to just take its random course. In about a millionth of a second, that negative electron will just fall right back into the positive hole. They recombine, they release a tiny bit of wasted heat, and our potential electrical current is completely lost. Moving on to Section 3, doping, P-type and N-type. This is how scientists solve that exact problem. To fix the equilibrium issue, scientists engineered a brilliant solution called doping, which involves intentionally introducing specific atomic impurities into the silicon lattice to alter its electrical properties. Think of it like strategically adding carbon to iron to make strong steel, but here we're doing it to perfectly control electricity. This creates 2 distinct flavors of silicon. On one side, we have P-type silicon. By introducing boron, which only has 3 valence electrons, we intentionally create a lattice with missing bonds or positive holes. On the flip side, we have N-type silicon. Here, we dope the silicon with phosphorus, which has 5 valence electrons. 4 of those bond with the silicon, leaving 1 extra unbonded, negatively charged free electron. So now we have one material packed with positive holes and another packed with negative free electrons. And that leads us right into Section 4, the p-n junction.
The real magic happens as soon as these two altered materials physically touch. It triggers this chaotic, microscopic event. Like floodwaters breaking through a dam, the free electrons from the N side rush across the border to fill the empty holes on the P side. But as they move, they leave behind the stationary atomic nuclei of their dopants. These are charged ions locked into the crystal lattice. This mass migration creates a central depletion region right at the boundary. It's essentially a no man's land, completely stripped of free charge carriers.
Now, as a result of that intense diffusion, by leaving those charged ions behind, a positive charge builds up on the N side of the junction and a negative charge builds up on the P side. This spatial separation of static charges basically acts like a battery built right into the crystal itself. It establishes an incredibly powerful, permanent internal electric field across the junction. This field acts as a sort of electrostatic barrier, preventing any more electrons from crossing over. It's a one-way turnstile, and it is perfectly primed for action. So, our microscopic engine is physically built and waiting. But just like a car needs gas, this engine needs the right fuel. In solar terms, this comes down to the band gap. For crystalline silicon, the band gap is exactly 1.1 electron volts. Photons with less energy than this, they just pass right through the material or create useless heat. But photons carrying at least 1.1 electron volts of energy have the exact power required to kick an electron out of its bond and into a state where it can flow as usable current. All right, Section 5, generating electric current. Let's press play and watch this thing go. With the sun shining, the process happens in rapid, beautiful succession. A photon strikes the silicon near the junction. Boom! An electron is knocked loose, creating an electron-hole pair. But remember how we said they usually recombine instantly and waste their energy? Not this time. Because they were created near our PN junction, that powerful built-in electric field immediately grabs them. It violently sweeps the negatively charged electron one way toward the N-type layer, and the positively charged hole the other way toward the P-type layer. This internal electric field essentially acts as a steep, slippery hill. Once the electron is pushed up to the N side, the electric field prevents it from sliding back across the junction to recombine. So, the electrons get trapped on the top surface of the cell, building up this massive negative charge, while the holes are pushed to the bottom. Boom! We have officially converted the energy of a photon into a stable electrical imbalance, a true voltage potential. Now we just have to give those trapped electrons a path. By attaching metal contacts to the top and bottom of the cell and connecting them with a wire, the electrons finally have a way to return to the positive side. But to get there, they have to flow out of the solar panel and through our external circuit. This is where they actually power your lights, run a water pump, or charge a battery, before finally flowing back into the bottom contact to recombine with the holes. This continuous, elegant sorting process will run the entire cycle over and over again, generating usable direct current literally for as long as the sun is shining. As we zoom back out from the atomic level, it really leaves you marveling at the sheer scale of this technology. I mean, we are taking an invisible, microscopic quantum dance, electrons being knocked loose and swept across a manufactured atomic barrier, and we're scaling it up across vast fields of glass to power entire cities all over the globe. No moving parts, no noise, just the pure, silent conversion of light into life-sustaining energy. It really begs the question, as we push these atomic architectures to even higher efficiencies in the years to come, just how much of our global energy future will be entirely solid state. Thanks for joining me on this explainer today, and keep wondering.